So I will speak about relaxation in unitary quantum circuits in thermodynamic limit. An example would be a random circuit. So a setting that has been, an old setting that has been studied many times. Might look even a bit dull, so what is there new to report about it? But I will try to convince you that under certain conditions, physics is rather interesting, so relaxation will not be straight exponential decay, as one might think. And this will be connected with some interesting mathematics, connected with non-hermiticity. But let me start with a simple question, namely, under what conditions can one have situation where a small change in a parameter leads to a large change in system's properties? In particular, I would be interested in the divergence sensitivity, like in a phase transition. And so I will give you a cartoonish sketch that there are two different situations where such divergence sensitivity can happen. So let's suppose we have a linear operator, A. You can think of it as being some finite matrix, and suppose it's diagonalizable. So we can write spectrum decomposition. So eigenvalues lambda j, and right and left eigenvectors. I'm deliberately keeping left and right eigenvectors as different ones because for non-Hermitian operators, this is how it is, and non-hermiticity will play an important role. So now let's add small perturbation of strength epsilon, and V is just some bounded, say, of norm 1 operator. And then let us have a look at some object, for instance, right eigenvectors, how much they change under this perturbation. And as everyone knows, this is what you get, right? So matrix elements of your perturbation divided by the differences of eigenvalues. And so you can bound this as this ratio. So in the numerator, the norms of eigenvectors, in the denominator, the eigenvalue differences. So now we would like to understand, now we want this object to diverge, right? And there are two different cases, roughly speaking. One is when the eigenvalue difference goes to 0, so which would be like a phase transition, gap closes, and you get what everyone knows. But there is a second choice, namely when the norms of those eigenvectors go to infinity. So this is much discussed, like phase transitions, and I will speak about this case. And as you immediately see, if one has a Hermitian operator, then those two guys are norm 1, so nothing strange can happen. But in non-Hermitian operators, it's different. Feel free to stop me at any point and ask questions. OK, so the setting will be that of relaxation, just unit evolution. You can think of starting with some product initial state. One of the objects that I will discuss will be entanglement. So you start with 0 entanglement, and then provided this evolution is generic, you will end up, due to typicality, in some typical state which can be described by properties of a random state. So entanglement will go from like, say, 0 entanglement to very high entanglement here. And what I would like to understand, how this process of relaxation goes about. For instance, what is the relaxation timescale, and so on. I will look at two objects. One will be purity, trace of the reduced density operator square, which measures entanglement of a pure state, as well as out-of-time ordered correlation functions, AUTOC. And so here is a sketch how one would expect this purity to behave. So we started with the product state, so purity is 1. So and then at long time, so this is semi-log plot. At long times, you will end up in a random state, and random state has a lot of entanglement, which means very small purity. And so you would expect now this decay to be like exponential relaxation towards this long time random state purity. And what I will look to see this relaxation a bit more clearly, I will look at purity at finite time minus this asymptotic purity of a random state. So this should look, this we expect will look like exponential decay, so this blue decaying curve. It turns out that actually under certain situations it can be quite different, like the way it's shown here on the right plot. So at certain point, at certain time, there is a kink, so that one has a different rate for longer times compared to initial decay rate. So this is semi-log scale. And standard theoretical analysis of this problem, I will show you how, would suggest that correct decay will be that one, the asymptotic one. But now the point is that the transition point between these two regimes is extensive in the length of your system, nth number of qubits that I have. And so in the thermodynamic limits, this point goes to infinity. And so correct thermodynamic relaxation rate is actually this initial one. So this is a sketch of physics that I want to discuss. Okay, so here is an outline. First, I will show you how this phenomenon just numerics in a Floquet system. So a circuit where you pick a Fisk gate and then you repeat it in a certain pattern. Second case will be that of random circuits, where you can describe average dynamics of purity or autok, so that one is dealing with a Floquet system on average. And then particularly simple case will be that of a random circuit where 2-qubit gates are Haar random, where some exact solution is possible. So in this setting, actually what one has is purely unit evolution. Then under averaging, one ends up with some Markovian description of, say, purity evolution. And this will bring us to some Toeplitz matrix, which is non-symmetric, non-Hermitian, and has interesting properties. And we will see that it will be, to understand the phenomenon, it will be interesting to be aware of the difference between the spectrum of a non-Hermitian operator of a finite matrix and the spectrum of an operator. So in thermodynamic limit, if you want like infinitely sized matrix, the spectrum of that object is completely different than the spectrum of finite sized matrix. And this will be a resolution of this strange decay that I will show you. Okay, so first Floquet circuit, just I'm sure everyone knows about it, but just to set the stage. So we started with the product initial state. You pick some fixed 2-qubit gate. For instance, this is one example, such XZ Heisenberg-like interaction. And then you add some magnetic field just to break integrability, so that your evolution is then completely generic, if you want, in colloquial terms, chaotic. And then you repeat this gate on all nearest neighbor gates in a certain order. So the propagator for 1 unit of time will be a product of all nearest neighbor gates of this form. Here are two examples. One would be you apply all those gates in this so-called brickwork or brick wall configuration. And another one down below here is so-called staircase configuration. So in both cases, 1 unit of time would be applying all gates on all nearest neighbor pairs of qubits. So this would be 1 unit of time. In the staircase, that would be 1 unit of time. And then you repeat this. So propagator for t time step is just the simple power of this unitary. And then you calculate purity, for instance. And here's what you get. Again, semi-log scale. What is shown is 3 different system sizes. And also I'm showing just finite time purity minus asymptotic purity which you have analytical expression, because that is just the purity of a random state. And now you see when you increase system size, then it becomes quite apparent that initial decay is different than the asymptotic one. There is a kink here. So this transition point, as I announced on the first slide, will move in thermodynamic limit n to infinity, will move to infinity. Yeah. So this was for brickwork circuit. For the staircase circuit, you get similar behavior. Note that in this case, initial decay is faster, and then you get slower decay. In the second case of a staircase circuit, initially you get slower decay and then faster. And again, transition point moves to infinity. So it's extensive in the number of qubits that you have. So this was Floquet circuit. And you get similar physics also for random circuits where some analytical simplification is possible. So random circuit is just, again, a quantum circuit when each individual gate is a random gate. And within the same mathematical framework that I will show you, you can discuss two different cases. This gate can be either completely hard random, so say if we are discussing qubits, it's just a random U4 unitary. Or you can have a situation where this guy, so 2-qubit gate, is composed out of some fixed 2-qubit gate, for instance, like the one I showed you on the previous slide, plus random single qubit unitaries. So having randomness just in single qubit unitaries is enough for everything I will show you. And then again, you repeat in a certain order, like this brick wall or a staircase. Now that there are different reasons why one would study random circuits. Like a long time ago, almost 20 years ago, the initial motivation was to study how fast you can generate entanglement. And already this paper by Emerson and company, they also did numerical, real experiments on NMR, like I think 5 qubits, something like that. More recently, interest comes also from understanding many-body physics, like spreading of operators, and also in like supremacy experiment. Google supremacy experiment actually used a random circuit. Okay, so now let us have a look at how one can simplify average evolution under such a random circuit. So there are different approaches. Let me sketch you the first one. Okay, so we would like to understand purity, which is trace of rho square. And the way to get average in dynamics is you express your density operator in terms of some local basis, for instance, products of Pauli matrices. So this sigma alpha is now just the product of Pauli matrices on different sides. Yeah. And C alpha is just expansion coefficient. And then you can write expression for the square of your reduced density operator after applying one 2-qubit gate. You get something like that. So there is a summation over all alpha and beta here in this line. And you can see that, so this is everything is exact. And you can see that rho square after one 2-qubit gate depends on all C alpha, C beta. But now after you do averaging over single qubit unitaries, what you end up is the following evolution. So namely, the squares of coefficient after one gate depend only on squares of coefficients on the previous step. So you get Markovian evolution of average squares of those expansion coefficients. So you can think of this C alpha squares as just some probability. I mean, indeed, they are probabilities because trace of rho should be 1. Yes, so sum of those coefficients squared should be 1. And this mapping goes back to Plenary and company, like many years ago, 15 years. As a side remark, interesting side remark here is, I mean, note that now this, okay, it's nice that you have Markovian description, but this Markovian matrix is still exponentially large. The size is actually 4 to the power of n, if you have n qubits. Lives on operator space. But you can do some reduction actually, and in some cases you can show that this Markovian matrix is actually equal to some integrable spin chains, and from there you can actually get the decay rate for certain circuits. I will not speak about that. There's a more recent sort of equivalent but nicer setting that I will use. Namely, here you have a mapping of squares of expansion coefficients. So to get purity, you have to, at the end, still do some sum of those expansion coefficients. But you can write the mapping directly for purities. So basically, you define some abstract Hilbert space denoted by this bit string label S, with expansion coefficients being purities for all different B partitions. So for instance, just to give you an example, suppose you have 5 qubits, then a bit string like that would denote a B partition where in the subsystem A you have all bits with zeros, so the first one and the third one, whereas in the subsystem B you have all the other 3 qubits. So in a single abstract vector phi, you encode purity for all different B partitions. And again, average evolution of this guy is governed by sort of the same Markovian matrices here. There is just some similarity transformation between the two. So in this setting, basically purity at time t is simple power of this Markovian matrix acting on the initial vector of purities. And if you start with initial product state, then initial vector of purities is just all purities are 1, because completely factorized state has 0 entanglement, so purity 1 for all different B partitions. Okay, and just to give you a flavor, here is an example of how those Markovian matrices look like. So for instance, if you take a setting where your 2-qubit gate is composed out of a fixed 2-qubit gate, for instance, this XX, or you might call it XY gate, plus random single qubit unitaries on each qubit, then Markovian matrix describing such 2-qubit transformation is just this 4x4 matrix written here. So it's actually symmetric and real. Now to get Markovian transformation for the whole circuit in a given configuration, for instance, for this staircase configuration, you just have to multiply those 2-qubit Markovian matrices in the same order that you apply your gates. And that gives you Markovian evolution governing your purity evolution for given circuit. Okay, now this Markovian matrix has one eigenvalue equal to 1. Corresponding eigenvector is just this asymptotic state reached at large time, which is just which has purities of a random state. So this, you know, what is this eigenvector? And then there will be a second largest eigenvalue, lambda 2. And so you would expect now that purity will asymptotically at long times decay as the second largest eigenvalue to the power of t. And there is a finite gap. Yeah? So between 1, this trivial invariant state, and the second largest eigenvalue, lambda 2, there is a finite gap, also in thermodynamic limits. So this gap does not go to 0. And then you can pick a gate, for instance, pick a circuit, like brick wall circuit with periodic boundary condition for certain parameters. You can even get analytical expression for the second largest eigenvalue. And then you can compare with numerics. Just iterating this Markovian chain, you can calculate how purity goes, evolves with time, and this is shown in this smaller plot. So let us have a look first at this one. So what is plotted here is I'm plotting minus log of I minus I infinity. So now minus log of purity increases. And this lambda 2 here is basic. So so again, for different system sizes. And you can see that initially you have some slope, and then you go over into slope actually given by this lambda 2. In order to see this more clearly, in the main plot, I'm now showing you a local slope of this purity decay. Yeah, so just local derivative. And the dashed line here is equal to lambda 2. And so you can, and in this scale time, I'm showing time scaled by the length of the subsystem A, which in my case is just n over 2. I take half-half bipartition. And you see that indeed, after sufficiently long time, indeed the decay rate will be given by lambda 2. But then if you take, I don't know, 34 qubits, you see some deviation at short times. So initially we actually thought that this is just some finite size effect and it will go away. But then when you look at larger systems using, I don't know, TBD to evolve such a large system, you in fact find that actually you start to deviate from this lambda 2 decay more and more. And in thermodynamic limit, actually you expect that this decay rate has a sudden jump at certain time. And so now the question is, I mean, how come? Why is asymptotic decay not given by lambda 2?
Can I ask a question?
Yeah, sure.
So why do you keep referring to lambda 2? Lambda 2 is the second largest eigenvalue?
Indeed.
And you have this, what is it?
And there is a gap. So there is a largest eigenvalue,
which is 1?
Equal to 1, yeah. And the second largest eigenvalue in modulus is this lambda 2.
And so you want to study relaxation. So this is decaying. It's telling you how the second dominant eigenvector rushes away, right?
Yeah, exactly. So if you now imagine your spectral decomposition, right? So m to the power of t will be just lambda j to the power of t. And so at sufficiently long time, all the other guys will decay, like lambda 3 and larger ones. And so you expect lambda 2 to be the only surviving contribution. That's why you expect.
But this is for the case where you already took the average over 1 qubit density.
Indeed. So yeah, good point. So everything I'm explaining here is for average purity. Yeah, averaging over my randomness in single qubit unitaries. Yeah, here.
And so
all the gates are independent in time and in space.
Right. Independently random.
Independently random. Yeah, IIDs all.
But then when you said that you use some method to simulate long times, you mean for the effective system that you get?
Exactly, yeah, just for the effective system, yeah,
okay,
for this M. Okay. I'm just simulating this Markovian evolution.
And do you have an intuition what the dominant eigenvector, the eigenvector corresponding to lambda 2 is?
For the exact solution that I have, in a few minutes I will show you what it is. Yeah.
Excellent.
In this case, I don't know from the top of my head. Yeah. And to add a comment on the randomness. So for large systems in thermodynamic limit, actually everything gets self-averaging. So even on one realization of your random circuit, single shot, you will get almost the same results as here. So kind of this randomness is not really essential to see any of the physics I'm explaining. It just kind of eases up analytical treatment.
Can I just ask for a clarification? Yeah. So if I look at the inset, the smaller plot,
yeah.
If I understand correctly, this is exactly what you said earlier, that there are two slopes, and there's a time scale on which you go from one slope to another. That's what we're talking about, right?
Yeah. So this is this.
And if I wanted to look at the red equation there, the naive sort of a mathematical, because all you're doing is you're applying power method, right? So the naive mathematical thing is that there's a lambda 3, and lambda 3 and lambda 2 are close by, and for some reason one of the coefficients is very small. Is that basically the intuition is that the amount of time you need to detect the true next eigenvalue is long because its coefficient is, even though it's exponential, like if you have two exponentials, no?
Yeah, no.
I'll let you explain it. I'm just trying to.
That's what I would also think. Yeah, but the explanation will not be of that kind. Yeah, this will not be behind the problem. Yeah, Because, for instance, let me perhaps go a few slides back to show you. Yeah, for instance, in this case, right, in the second case, here initial decay is slower. Yeah? So as there would be some eigenvalue of modulus larger than lambda 2. Yeah? So if what you are saying and what I would also expect, then somehow I couldn't see this slower decay, because there is no eigenvalue larger than lambda 2.
So I can't fake it with an almost small prefactor. Okay.
Yeah, but explanation will involve prefactors. I'll show you in a couple of slides. Yeah. Any other question? Yeah. So. Okay, so far the point being that the rate is not always determined by the second largest eigenvalue. And I should have mentioned the work I'm reporting has been done together with my PhD student, Yash Binsa. And recently there have been related or similar observations that the gap does not necessarily give you a relaxation time in the context of Lindbladian evolution by various groups. Takashi Mori and company, Ueda and Clerk. And let me now give you a sort of sketch of how this can come about. Again, we will go back to the spectral decomposition. So we have now our Markovian matrix, left and right eigenvectors. And when you iterate m to the power of t, you just get this. And with expansion coefficients Cj, which are just projections of your initial vector of purities, which is just the vector with all ones, if you remember, all purities initially are 1, on left eigenvectors. Now, you will remember for non-Hermitian operators, you have B orthogonality relation, right? Lj inner product with Rj is delta, jk, taking two different ones. But the left eigenvectors between themselves, nor right eigenvectors between themselves are orthogonal. So it can happen, actually, that, for instance, in thermodynamic limit, they get less and less orthogonal. In other words, this left basis or right basis, there can be a bunch of eigenvectors which gets more and more collinear. And this means that as a consequence, the expansion coefficients here, Cj, can grow as you increase system size. They can actually become exponentially large. And here is one explicit example to really show you how the spectrum looks like and how this strange decay can come about. So taking a particular gate doesn't really matter, staircase configuration, open boundary conditions. So here is a spectrum for very small system so that you can see individual eigenvalues. So there is one eigenvalue equal to 1, this guy here. Corresponding eigenvector is just the steady state, this trivial that we know. And then there is a bunch of eigenvalues which are almost degenerate in modulus. So those are like lambda 2s. There are of order n of them. But they have different phases. So eigenvalues are in complex plane, because we have non-Hermitian operator. And then there is actually bulk of eigenvalues here. So in this case, like lambda 3 in modulus is much smaller than lambda 2, for instance. And you can just forget about them. And so again, looking at this, and what I'm writing here now, just focusing on those eigenvalues which are degenerate in modulus. So like of order n of them. They're almost on a circle, so the phase increases in equal intervals. And so what happens is that, I should say, lambda 2, the modulus of lambda 2 is just 1 over 4 in this case. Yeah? So let me perhaps use this one. Whereas, in fact, purity decays as 1/2 to the power of t. I'm not showing you numerics, but you can trust me. So in this case, we are dealing with a situation where initial decay is slower than the one predicted by this lambda 2 here. And so this comes about, here you can see just numerical calculation of this sum that I'm writing here in the round brackets for different system sizes. And what you can see here, that initially up to some time, which again scales with system size, the sum in round brackets here sort of mimics exponential function, like 2 to the power of t. Yeah? So for instance, looking here at n equal to 12, yeah, this sum that I'm showing you here basically oscillates, but on average grows like an exponential function to the power of t. And then, of course, at some time, which is extensive in n, like n over 2, again decays and then just repeats. And so it means that this sum, which is 2 to the power of t, partially cancels 1 over 4 to the power of t, and that is how you get this 1/2 to the power of t. So it looks like there would be, there is lambda 2 here, and it looks like there would be like a phantom fake eigenvalue of modulus 1/2. So that's why we call this a phantom relaxation. And it comes due, again, because those expansion coefficients can grow exponentially in thermodynamic limit. So this is purity. The same thing happens also for out-of-time ordered correlation functions. So here is just the definition of OTOC, just the norm of the commutator. It measures spreading of operators between site 1 and j and two given Pauli matrices. These indices alpha and beta of what kind of Pauli matrices you take are not really important. For long times, this OTOC, the way I define it here, will go towards 1. And because we would like to understand the relaxation of this OTOC, what we will look at is 1 minus this O, so which means just this 4-point correlation function. And the way this OTOC behaves is sketched here. This space-time diagram, color denotes the value of OTOC, and if we look at the cross-section at some time, you get the picture sketched on the right here. And so you can see that, zoom in here, different colors are different times, and you see that as time increases, at fixing a site, for instance, site 6, this OTOC will approach 1, and we would like to understand how fast you approach asymptotic OTOC value. And also you can see that OTOC is again quadratic in time evolved Pauli matrix, similar as purity. So it comes as no surprise that also this average dynamics of OTOC will be given by the same Markovian matrix. There is just some similarity transformation. And so, not very surprisingly, you see also this two-step relaxation with the kink also in out-of-time ordered correlation function. So here is again like two-dimensional plot, spatial index k and time index t. And what is plotted on the right-hand side is just the cross-section at fixed k. So I'm looking at OTOC between site 1 and 4, and then as a function of time, which is shown here. And you can see that initially in this region, we have decay with certain rate. And then from this point onward, decay is faster. And this faster decay is the one given by lambda 2, whereas the initial one is slower. Okay, so far it was just numerics, so now let us look at one case when one can get some analytical understanding because one can do this spectral decomposition exactly. And this is the case when 2-qubit gates are, actually you can treat any local dimension q dits with d-level system, not just qubits. So 2-qubit gate is here just completely random. In this case, a 2-qubit Markovian piece has the following simple form, where parameter alpha just depends on local dimension d. A sort of side observation, which we are not able to use, but it's kind of gives you a geometrical picture of what this 2-qubit guy does. If you do singular value decomposition of this matrix, you just have two non-zero singular values. One is 1, and another one is slightly larger than 1. Depends on the local dimension d. And so you can visualize action of this two-side transformation as being first projection on a plane, and then along one direction corresponding to the singular value, which is slightly larger than 1, you stretch a little bit, and then you rotate. This is just interpretation of this singular value decomposition. And then taking a staircase configuration, you just repeat this operation on all nearest neighbor qubits. So it's like project, stretch, rotate, project, stretch, rotate. Now in this case, you can do some further simplification of the Markovian process. Namely, if you limit yourself just to purities with consecutive qubits. So there are 2 to the power of n different B partitions because each qubit can be either in A or B. But if you now limit to purities where you have first k qubits in A and the rest in B, then those purities decouple from the other. And you get a simple recursive relation. So this Ik is now denotes purity for where subsystem A is composed of first q qubits. And you can write this simple recursive relation in a matrix form, where A is just some shift vector, it's not very important, and the important part is this matrix T. Now T is just of size n by n. Yeah, so we have reduced our problem from the size 4 to the power of n to n by n, which is very nice. And on top of it, this T has very, nice form. It's a Toeplitz matrix. Toeplitz matrix is a matrix where elements on all diagonals are the same. So each diagonal has the same element. So in this particular case, the main diagonal alpha square, above the diagonal alpha, then everywhere zeros, and below diagonal you have increasing powers of alpha. And you can find the spectrum of this matrix exactly, as well as left and right eigenvectors, just some Chebyshev polynomials. It turns out that left and right eigenvectors are localized at the edge. Left eigenvectors on the left edge, right eigenvectors on the right edge. This is what is called non-Hermitian skin effect. It's like very sort of much researched topic in the last 4 years or something like that. So they have like exponentially small overlap, which means that in thermodynamic limit, a bunch of those left eigenvectors must become more and more collinear in this sense, right? Because they are all bunched at one edge. And the localization length of those eigenvectors is basically determined by this alpha. Yeah, so it's like fixed. Yeah.
What do you mean by this overlap being exponentially suppressed when, by definition,
sorry. I see. I'm always confusing people with this. Yeah. So of course this. So I'm just trying to say that one of the two is localized at one edge, the other one on the other edge, right? Of course, then you normalize them so that the inner product is equal to 1, yeah? And for instance, on top of it, you can also normalize, I don't know, right eigenvectors to be of norm 1, which then implies that the norm of left eigenvectors will be exponentially large. Yeah. Or if you would take other normalization condition, right, normalizing right and left at the same time, then of course this overlap would be exponentially small. So you always get some exponential factor in one way. Yeah. Okay. So, but So we would like to now understand how iteration with this Toplitz's matrix produces your purity decay. And actually, you can solve this recursive relation. So even without looking at the matrix, you can solve it in the leading order. And this is what you get here. So you get that for times larger than some critical time, which is proportional to n, you have decay with so-called phantom eigenvalue given by this expression. And you can also get exact expression for lambda 2, which is different. Now still, of course, question remains. I mean, here we managed to get this true thermodynamic decay just by brute force solving a recursive relation. But still, one would like to understand where does this lambda 2 come from. Yeah. And, well, here is how it goes. So what I'm plotting here is now the spectrum of this Toplitz's matrix that I'm discussing. Yeah. And it turns out that the spectrum of T is actually real. Despite the matrix being non-symmetric, it's real, just this. So in a complex plane, these are just, in the thermodynamic limit, just this red interval here. But now if you look at the spectrum of operators, so mathematicians tell you how can you get the spectrum of appropriate Toplitz's operator. I mean, there is a nice theory of Toplitz's operators. And it's actually very simple. So what you have to do to get the spectrum of the operator, so like the quote-unquote infinitely large matrix, is you have to calculate what is called a symbol of your Toplitz's matrix, which is nothing but the Fourier transformation of your matrix elements across the other diagonal, which for a physicist would be, if you would have periodic boundary conditions, then this would be nothing but the Bloch Hamiltonian. So because you can actually interpret this Toplitz's matrix as nothing but a tight binding model, yeah, where you have asymmetry between the hopping amplitude of hopping to the left and to the right in such a way that, if I show you the larger one version here, right? So there is on-site energy alpha square, then there is a hopping amplitude of alpha of hopping one side to the right, but to the left you can hop with amplitude alpha 3 by one side, alpha 4 two sides, and so on. So just tight binding model. And then doing Fourier transformation, you get Bloch Hamiltonian, and this is what is called this symbol. Yeah.
Just to check, so this is for the staircase circuit?
This is for the staircase.
So that's where the asymmetry comes from?
Yeah, in this case, for purity decay, this is where you get this kink-like relaxation. I will comment on the brick wall if this is your next question. Yeah. All right, so you get this whatever symbol, and you can plot the spectrum. And the spectrum is then just the, on this sketch, is this oval-shaped, lemon-shaped figure, I mean, or here. So the spectrum of the operator is whole this elongated disk. So you can see that the spectrum of every finite matrix is this real interval. And it's completely different than the spectrum of the operator. So the spectrum is completely discontinuous in thermodynamic limit. Because naively one would perhaps think that just increase the size of your matrix and you should somehow approach the spectrum of the operator. It's not like that. For non-Hermitian operators, it can happen that this is not the case. But then mathematicians also tell you what is the object that is continuous, that is stable. And this is something called the pseudospectrum. So pseudospectrum of an operator is simply, I mean, there are various equivalent definitions, and there is a nice book about it. One of the definitions is simply, well, take your matrix operator, perturb it a little bit, so plus epsilon times some E is here just a matrix of random numbers, say Gaussian, with zero mean, variance 1. And eigenvalues of this, taking the limit, and this is important because the order of limits does not commute, taking first the limit of n to infinity at fixed epsilon, this will converge. So the spectrum of this perturbed matrix is well defined and is called the pseudospectrum. And if you calculate pseudospectrum, this is what you get. This is just sketched here. So here I'm taking just single perturbation. Yeah? So there's single random matrix with certain epsilon, 10 to minus 15 here. And if I take n20, I get the spectrum which is very similar at the spectrum of my t. But when I increase system size 100, 500, I converge to the spectrum of the operator, which I got exactly from this symbol. And now if you look at the norm of the spectral norm here, norm of the operator, or if you want of the pseudospectrum, this number 3/7 is exactly the phantom, lambda phantom that I have shown you here. So it's actually not lambda 2. It's not the second largest eigenvalue that gives you this decay rate, but it's the pseudospectrum, or the spectrum of the operator if you are able to calculate it. So in a funny way, one could say that if you are exact, meaning that if you calculate the spectrum of precisely your t, this gives you wrong answer, wrong decay rate, because it gives you this lambda 2. But if you are a bit sloppy, if you have some numerical inaccuracy, and you calculate a spectrum of slightly perturbed matrix, meaning you are calculating pseudospectrum, you get the correct result, this lambda phantom.
A quick question about that, though. So in an earlier plot, you did show that eventually it seemed like lambda 2 did ultimately dominate.
Indeed.
So what's the reconciliation of that with the idea that lambda 2 is not the right thing? How do you?
Right, out of that, it's not very clear. One would have to do this spectral decomposition and look at coefficients. Because I guess this must depend on how this expansion coefficients scale with system size. And somehow it must turn out that this transition time is like n times some.
That time gets longer, you think?
Indeed, that's important, Because, this is one of the important points, If this time would be finite, then this would be nothing surprising, You just have some different decay initially, but then it's really lambda 2. The point is that this transition time goes to infinity. It's proportional to n. So because then you can conclude that correct relaxation time in thermodynamic limits, which means first system size n to infinity, and only then time to infinity will be this first decay. Okay, so let me just conclude and perhaps also comment. If you take a brick wall configuration, not the staircase, for this purity thing, then what you end up is, again, this T matrix, which in this case is just symmetric 3-diagonal. So Hermitian and nothing surprising happens. Okay, so here is a slide with conclusions. I will just say that perhaps take-home message is if you are dealing with non-Hermitian matrices like transfer matrices, Markovian processes, and so on, be careful. Sometimes it can happen that lambda 2 will not give you correct decay. It comes about because limits L to infinity and T to infinity do not commute. This is actually often the case, whatever you look at. Behind is exponentially growing expansion coefficients, so you really need many body system n to infinity. And it occurs in many situations, like random circuits, where some exact solutions are possible, or even Floquet system, so no randomness, just you repeat simple gate, the same simple gate, and you can have situations where this happens. I will stop here, and thank you.
Okay, thanks a lot. Any questions for Mark?
So there are examples of circuits, those with U1 symmetries, where the decay of the purity becomes a stretched exponential. Have you thought about how those fit into this?
Yeah, I have no idea. We have not tried it neither numerically and also like analytically, then of course this doesn't go through. So yeah, it's a good question, I don't know. I don't know. I would expect that perhaps you could still have this. But
I guess either the actual spectrum or the pseudo spectrum should be gapless, but it's not obvious which of the two.
Yeah. Yeah. No.
Very last thing, I think you said there was no anomalous behavior in the brick wall case.
Yeah.
But you still have a kink, don't you? Is that right? Or was the kink only in the...
Well, yeah, okay, let me explain. So, actually, if you ask me, can I tell you where do I have this two-step relaxation and when not? I'm not really able to give you a rule. Yeah? I can give you a list of situation circuits where you have it and where you don't have it. And then, for instance, for purity and Haar random gates, you don't have it for brick wall, you have it for staircase. If I would look at OTOC, and again, Haar random circuit, this nice circuit, I would have it for brick wall with periodic boundary conditions, but not for brick wall with open boundary conditions. So it's kind of, yeah. What one can say that one will typically see it in cases, and this goes also to connection with this non-Hermitian skin effect, one will have it in situations where you have large sensitivity to small perturbations. For instance, where OBC and PBC, periodic and open boundary conditions, will behave differently. And this is well known in the context of non-Hermitian skin effect, that this is kind of behind it.
The purity relates to the Renyi entropy of order 2. Is there anything similar for Renyi 4 or Renyi 3 or any other Renyi entropy?
Yeah, thank you. Good question. Yeah. So we have looked just numerically at von Neumann entropy. So if you look at similar analogous with von Neumann entropy, you also see kink. I don't have a picture here, but I would expect it that you will also see it for higher Renyi entropies. And actually, in some cases, we did check, and you do see it. So it's not particular to purity. Yeah. But this analytical treatment, of course, works just for purity. For other Renyi entropies, you would have to use some, I don't know, replica trick or some more complicated techniques.